Hello, my name is John Douglas, and today I'm going to talk about some cost-benefit analysis that we conducted within the Turnkey project to assess the potential of operational earthquake forecasting within Europe. So my co-author on this is Douglas and Azarbakht, and we published this work in Natural Hazards earlier this year. Okay, so first of all, some introduction to operational earthquake forecasting. So time-dependent hazard assessments have been made numerous times over the past 20 years for various locations. And sometimes these can show that there's a large change in the probability of strong shaking leading up to a large event. So this change in probability could be up to maybe 1,000 times in some cases. And this period of heightened hazard may also last for many months or just a few days. So operational earthquake forecasting tries to make use of this time-dependent hazard assessment to mitigate risk by improving preparedness. So mitigating risk means triggering certain actions. So some examples of these include making sure that you have emergency supplies at home, reinforcing earthquake drills, perhaps preventing the use of vulnerable structures, and maybe at the extreme end, evacuating the area subject to the high seismic hazard. So the question we wanted to answer was where in Europe would OEF, or operational earthquake forecasting, trigger cost-beneficial actions. So for this, we conducted a relatively simple cost-benefit analysis using a step function to define the fragility of losses, a step function to define losses. So in this assumption, if the ground shaking expressed in terms of peak ground acceleration, PGA, is below a threshold and no action was taken, then there wouldn't be any cost. If there was an action taken, then there would be a cost C. If, on the other hand, the ground shaking was above this threshold and no action was taken, there would be a loss L, which would be much higher than C. But if the action was taken, then all that loss would be mitigated and you would just have the cost of the action. So there's two variables in this part of the problem, L and C. So I'm going to talk about those in a following slide. So to estimate the ratio L over C, so in fact the equation only uses this ratio, so you don't need to define them separately, you can define the ratio. We considered some quite simple examples of actions that could be taken very rapidly during a period of increased seismic hazard. So one example is shown here. So in the 1994 earthquake in Northridge, these tanks containing fuel fell over during the shaking. This is quite a common observation in large earthquakes. As they were unsecured, they fell over. If they'd been secured, there wouldn't be they wouldn't have fallen over, and hence that any loss could be mitigated. So to estimate the loss mitigated, we assumed that there was, say, a building next to these fuel tanks, which have a value of $1 million. Which could be completely lost if the fuel tanks ruptured and caused a fire. And then we suggested that the probability that the cylinder would explode or catch fire when it falls is 1 over 100. So this gives us a loss which is potentially mitigated of $10,000. The cost of mitigating this loss could be as little as, say, $20. So this could consist of making a survey of the building to make sure there's no tanks, and to decide on how to mitigate the loss. Secure those, perhaps using rope to tie them together. But that during that period, you might not be able to use the product in containment in these tanks. So using this simple approach, you get a loss to cost ratio of 1 over of 10,000 over 20, so 500. So then we use the proposal of Gordon Wu from 2013 during the REACT project to express the benefit to cost ratio, which tells us whether the action is cost beneficial or not. And this is computed simply by the probability that the intensity measure, so in this case peak ground acceleration, will be above the threshold, with the potential could cause loss during the period of increased hazard, multiplied by L over C. So we've already talked about L over C. Now I'm going to talk about the other inputs to this problem. So the threshold PGA, we're using the fragility function defined in terms of intensity, macroseismic intensity. So for this we use the Caprio et al. 2015 PGA to intensity conversion equation, which is shown at the bottom, for 3 different intensities, intensity 5, 6, and 7. So these can be thought of as a fragility function. So if we have, we're interested in the median intensity of 5, this allows us to define the PGA equivalent to that, so it's 0.05 G, intensity 6 0.08 G, intensity 7 0.15 G. Then we need to define the probability P, that the observed ground motion will be above this threshold. So for this we use the European Seismic Hazard Model 2013, and then we multiplied that hazard curve by a probability gain, which I'm going to discuss on the next slide. And then the last input we need is the time D, which is the time period of interest. So generally this could be maybe a few days to perhaps a month, during which the hazard is increased. So this probability gain, what we did was we assessed this based on some values in the literature. So one of them was this study by Gulia et al. 2016, based on the L'Aquila sequence. And in this case, you can see that the probability gain, so the increase in probability of a serious shaking, increased from the long-term value to a value just before the main shock of a factor of about 1,000. So this was one of the inputs we used to define this probability gain for purposes of this analysis. So then we conducted a parametric study with various inputs. So we have these 3 different threshold PGAs, various probability gains based on previous studies, 2 time periods, 1 week and 1 month, and then various estimates of the L to C ratio of 10 to 10,000. So 10,000 means a very low cost action. And then we drew contour maps for various values of R, the benefit to cost ratio. So I'm just going to show you now to conclude some of these maps. So this is an example where there's a probability gain of 1,000, and we're considering a crisis period of 1 week, an L to C ratio of 1,000. So the areas in red, which covers most of Southern Europe, means that such a action would be cost beneficial. Areas in the north that are either green or white, that action wouldn't be cost beneficial. This is because even though the probability gain is probability of serious shaking is increased, it's still very low. If we then consider a much more expensive action, so an L to C ratio, which is now smaller, only the most seismic active areas in Europe would such action be cost beneficial. Finally, if we consider a much longer crisis period, so the seismic hazard has now will increase for over a period of 1 month, then almost all of Europe, such an action would be cost beneficial because there's much more chance that there actually would be strong shaking during this period. So just to conclude, seismic hazard varies with time, as been shown on numerous occasions. Operational earthquake forecasting has the potential to mitigate risk. And this study has shown that areas of high seismic hazards, such as the Mediterranean region, would benefit from OEF if the mitigation actions were sufficiently cheap. Costly actions are rarely cost beneficial, but if the increase in probability is very high or it lasts for a long time, then even areas of moderate seismic hazard could benefit from OEF. So for more information, you can have a look at our open access paper, which is shown here. Thanks very much. I'll be available for questions later on.